Alright, so in this video we're going to go over the basics of ionic bonding and covalent bonding. Alright, so anytime that we have a chemical bond, basically that is when you have atoms or ions that are strongly attracted to each other. So the reason that there is a bond is because of an attraction between the atoms or the ions. Now we have ionic bonds, which involves the attraction of ions together. So we have oppositely charged particles, and they come together because they are attracted to each other. So the positive attracts the negative. Sometimes this will involve the transfer of electrons. So if you have a metal atom and it becomes an ion, it will lose electrons, and then if you have a non-metal atom and it gains electrons, it becomes negatively charged. So you can have two atoms come into contact and they transfer the electrons, and then we have an ionic bond that is formed. But you can also have just ions that are already formed and they come together to create that attraction. Typically you'll see this with metals and nonmetals, but they will not always be metals and nonmetals. The reason we typically see this is because metals have a tendency to lose electrons while nonmetals will gain them. So you will usually see that in ionic bonds, but you also can have some ionic bonds that are not with any metals, like ammonium nitrate is where we have the positive ammonium coming into contact with the negative nitrate, and they're attracted to each other. So there are no metals here, but there is an ionic bond. So we'll always see a cation and an anion though. So the cation and the anion. Anions being negative, cations being positive. Now, a covalent bond is when you have two atoms that are coming together and they're attracted to each other because of the mutual attraction they have for electrons. So typically you'll see nonmetals doing this because nonmetals have a tendency to gain electrons. So in order for two or more nonmetals to gain electrons, they have to share them. Now, a metallic bond involves metals, and this is where we have the metal atoms bonding to each other. So a piece of gold is a metallic bond because you've got more than one gold atom in there. And what ends up happening with a metallic bond is that they all share electrons. The electrons are delocalized. They're free to move about from atom to atom. It creates an electron sea. So when we have a bond, so if we have two atoms coming together and we're trying to decide if it's going to be ionic or covalent, we will look at the difference in electronegativity. So every atom has an assigned electronegativity, and the difference, how great of a difference that electronegativity is, that will determine whether the electrons transfer electrons, or the atoms that transfer electrons, or they share them. So if the difference in electronegativity is great enough, you're going to get an ionic bond because one of the atoms is able to pull the electrons completely off of the other atom. So remember, electronegativity is the ability of an atom to pull electrons towards itself in a chemical bond. So if your electronegativity difference is great enough, one element's going to pull off the electrons. So usually that difference needs to be at least 1.8 for it to be considered ionic, but there are actually different set numbers, but we're going to go with 1.8 in here. So I'm sorry, 1.7. So it needs to be at least 1.7. Okay, so there are actually some compounds that are metals and nonmetals, and those bonds are not ionic because the electronegativity difference isn't great enough. They actually have more covalent character than they do ionic. Now, when we have an ionic bond that's being formed, okay, cations, which are positive, will come together with an anion, which is a negative ion. So elements that have lower ionization energy will lose the electron, or lose more than one electron, to get a full S and P sublevel. So remember, ionization energy is the energy required to remove electrons. It still requires energy to remove an electron. Nonmetals typically gain electrons to get that full valence shell, which is really just the outside S&P sublevel. And this is typically because they have a higher electron affinity. So electron affinity is the energy released when an electron is added to an atom. So nonmetals typically release energy and high amounts of energy when they gain electrons. And metals have lower ionization energy, which means that it only takes a little bit of energy to remove one of the electrons. So when they come together, you end up with a release of energy with most metals and nonmetals because the ionization energy is much lower than the electron affinity of the nonmetal. All right, so just to clear things up, atoms do not want electrons. They do not want to gain, they do not want to lose. There is no such thing as them wanting anything because they don't have emotions. Okay? Even though metals typically will lose electrons, you still have to put energy into this process. It doesn't happen naturally. It doesn't happen without that input of energy. Now, the size of the ions is going to be different than the regular atoms. So once they lose electrons or once they gain electrons, their size changes. So if they gain electrons, they get bigger. If they lose, they get smaller. And usually this process doesn't happen in one step. In order to go through this process of making atoms into ions and then making that ionic bond, well, you have to be in the gaseous state to lose an electron and also to gain an electron. And then you also have to separate diatomic molecules. So if you have something that's going to react to Cl2, you're going to have to separate those two chlorine atoms. Now, when we have an ionic bond, you will have more than one ion bonding together. It's not always going to be just one cation to one anion. It always has the same ratio. So if I have MgCl2, I always have 2 chlorines for every 1 magnesium, but they're going to form a crystal lattice, which looks something like this. So what you'll have here is you'll have the negative ion and it's surrounded by the positive, and then we have the next negative ion and it's surrounded by the positives, and then it forms this very ordered structure. They will position themselves in a distance that will maximize the attraction between the negative and the positive, and then minimize the repulsion that the negative is going to have for the negative and the positives are going to have for the positives. So that's why it will always be at a set distance, because we're trying to maximize attraction and minimize repulsion. All right, so when we look at ionic bonds, we will see that they have higher melting points and boiling points. This is because they have very, very strong attractions to each other. This is actually this is the strongest intramolecular force. So remember, intermolecular forces deal with the attraction of molecules to each other. Intramolecular forces are going to be in between the atoms of the compound or the molecule. Most ionic compounds are going to be soluble in water, and this is because they're charged. The charged particles are attracted to the polar water molecules, and that's how they're able to separate the ions. They will conduct electricity if the ions can move, so if it's melted or if you dissolve it into a solvent. So they need to be able to move. So if you have a solid ionic compound, it's not going to conduct electricity. So when we dissolve an ionic compound, what ends up happening is we've got these polar water molecules. Well, if I have my water molecule, here are my hydrogens, this is a positive end, and then my oxygen is negative. So we have 2 poles, so we have a dipole. Well, the positive end of the water molecule is attracted to the negative ions, and then the positive ions are attracted to the negative end of the water molecules. So that is how we pull the ions apart from each other, because they are attracted to the water molecules. So what ends up happening, it happens in 3 steps. We have to separate the ions from each other. We have to separate the water molecules from each other, and then we surround the ions with the water molecules. Now, ionic compounds are also brittle. Okay, this is because of their crystal lattice structure. So normally, you're going to have positive, negative, positive, negative. Well, if you put pressure on this and shift it down, and then you have the positive next to the positive and the negative next to the negative, well, then they repel each other, so it breaks. So that's why it's considered to be brittle. Now, lattice energy is the energy needed to separate the ions in an ionic compound. It's a measure of stability. So the higher the lattice energy, the more stable the compound. Now, lattice energy, because it deals with the attraction of the positive to the negative, it involves 2 things. So anytime that we're looking at charged particles attracting each other, that goes back to Coulomb's law. So that depends on the magnitude of the charge. So is it +1, +2, +3? And also how large the ion is. The closer the ions can get to each other, the more attracted they are to each other. So the smaller the ion is, the closer it can get to the other ion, which makes it a stronger bond. Now, we always look at the magnitude of the charge first, and then we can go and look at the size. All right, so let's look at the following compounds. We're going to put them in order of increasing lattice energy. So the first thing we do is we look at the charge. So lithium and bromide, that's a +1, -1. Nitrogen, that's a -3, so the iron has to be +3 here. And cadmium and oxygen, oxygen's -2, so the cadmium has to be +2. So the higher the charge, the stronger the bond. So we know that Fe(N) has to be greater than all the rest of them. Then I've got cadmium oxide and lithium bromide. Then it would be cadmium oxide. And then the smallest would be lithium bromide. So always look at the charge first, and then we can go and look at the size. All right, so let's look at these now. So let's look at the magnitude of the charge first. +2, -2, +2, this one's -1, and then +2, -2. Well, right away I can see this one differs in the charge, and the chloride has a smaller magnitude of charge. So that means that one should be the smallest. Then now we're going to look at the size. So we've got oxygen and sulfur. That's how they differ. Well, if I look at the periodic table, oxygen is higher on the periodic table. And then sulfur is lower, which makes sulfur bigger. So even though they're ions, they have the same magnitude charge, we can just look to see, okay, which atom would be smaller. Oxygen should be smaller, so that one should be the highest. So we always look at magnitude first, then the size. All right, so let's look at some basics of covalent bonding really quick. So covalent bonding happens typically between nonmetals, and that's because they both are, all of the atoms there want to gain electrons. The only way that they can all gain is if they share. So they attain a noble gas configuration, which really just means we're filling up that S and P sublevel of the highest energy level. All right, so we typically go with the octet rule. Most atoms do want to have 8 electrons to fill the S and the P sublevel. So carbon right here has 1, 2, 3, 4 bonds. For each bond is 2 electrons, so that's 8. Now, a single bond will be where we share 2 electrons. We can also have double bonds where we share 4, and a triple bond where we share 6. There's nothing beyond that. So when we look at the bond length of these 3, a single bond is longer than double, which is longer than a triple. And this will also change the strength too. So triple bonds tend to be the strongest bond, then we have double, and then single. So the shorter the bond, the stronger the bond.